Today we are glad to have Mr. Dan Kopin, who is the VELCO. VELCO stands for Vermont Electric Power Company. He's a VELCO's manager of innovation. He supports the development and acceleration of innovative initiatives that deliver value to VELCO, its customer owners, and Vermont. So he will talk about the interesting topic today. So we are glad to have him here. So Dan, back to you.
Excellent. Well, thank you so much for having me. A pleasure to speak with you all today and really appreciate the invitation. So greetings from Vermont. I'm going to talk about the frontier of grid transformation that's happening here in our state. What you're seeing on this slide is our new backup control center, which is actually designed to look like a barn. You can see our 345 and 115 kV substation right nearby. And the way that VELCO, we do our work, of course, is in close collaboration with our communities. And we wanted to make sure that in designing a backup control center for this area, we fit the character of the land. And that's really the way we do our work. And so that's our backup control center that we operate the grid from. So here we go. So I'll talk a little bit about VELCO, who we are, what we do. I'll share some steady state observations we're making, as well as some stability observations. I'll talk about the difference when I say those two terms, what I mean. And then I'll talk about FERC Order 901, the new requirements that are coming, as well as our plans to address those requirements. And throughout the presentation, I'm happy to answer any questions or save questions to the end. You just let me know what works best for you all, okay? All right. So VELCO, we were formed in 1956 when our distribution utilities joined together to create the first statewide transmission-only entity. Now we're the only entity in the country, that's formed in this particular way in which the distribution utilities actually own the transmission operator and planner. And the benefit of that is that our profit model is such that when we earn returns and we earn a profit, that actually goes back to the distribution utilities, and that is then used to decrease the retail electricity cost in the state. So it's a great model. It's had a lot of regulatory foresight went into designing VELCO that way, and it's proved to have significant dividends for Vermonters. I'm very proud of that. You can see our system is that's 738 miles of transmission, about 13,000 acres of right-of-way, 55 substations, but we have 1,500 miles of fiber optic networks. So we have lots of high speed communications technologies in there. And as a reminder to everybody, Vermont is located in New England. We're within the Eastern Interconnection. ISO New England is our reliability coordinator, balancing authority, planning coordinator. And we're actually a transmission operator, transmission planner that runs in parallel with the ISO, right? So when they have issues on their end or we have issues on ours, we provide redundant support to one another, which is very valuable. Here are 17 different distribution utilities in a GIS map that shows their different service territories. And you can see where we border with Quebec, New York, New Hampshire, and Massachusetts. So we're really at a critical juncture in terms of where the grid is today and where it's going moving into the future. All right, so I'm going to talk about some steady state observations. And what I mean by steady state, I'm talking about normal conditions. So that's really the basis of what I'll be sharing today. All right, so here's the total Vermont net load. This is from 2015. You can see here that the net loads that we experienced from March 2015 to June 2015, which is the period, they actually went as low as 450 megawatts. And that's by far just the lowest we would go. You can see our load during that time actually would go up to 900. We're about a gigawatt peaking system historically. And so what you're seeing here is really 450 is our lowest. But over time, as year after year goes on, you're seeing 2016, 17, 18, 19. There's more noise that shows up. And then COVID happened. As we can see, the net loads on the system start decreasing more and more over time. And we thought, with COVID, it's a fluke. Perhaps that's not going to start showing up. And sure enough, 2021, similar data. But then all of a sudden, as we recover, the data stays noisy. And we see the total Vermont net load reach as low as almost 100 megawatts. And we're expecting negative net load on the system. So that's typically what a lot of presentations talk about are the net loads, but I have some data as well just to show about reverse power flow from distribution to transmission. And here are 4 transmission distribution interfaces. So we're talking about power flow from the low voltage system back onto the bulk electric system, the 115 kV system. So here's what ended up happening 2015, same timeline, same time frame, year after year. And you can see, solar comes up. But what's pretty remarkable about the pandemic and what happened was that it spread. So more and more of our transmission distribution interfaces started experiencing this backflow. And again, I just want to emphasize what you're looking at here are backflows that are happening consistently across our network year after year, not just right down to transmission to distribution, but now from distribution back to transmission. So in summary, you can see total Vermont net load from 2015 going to 2024, and then from 2015 going to 2024. So that's what's happening here in the state. This is a great slide from New England. ISO New England gets full credit for this. You're seeing what they're expecting to be the estimated reduction in net load from behind the meter PV. As that occurs, what is the true load at this particular time, right? That 12,000 megawatts for the purposes of this diagram is going down further and further over time. And so we're expecting within New England, the same trend that Vermont is experiencing. We have a true net load or true gross load that is at 12,000 megawatts. But as over time DG comes online, we're expecting to reach below 2,000 megawatts. This is, I think, my favorite slide from ISO New England. It is very clear, it's simple, but it's very powerful. So we take the slide, right, that we had right beforehand, and we talk about, okay, what does the net load decrease really mean? And then you overlay New England's nuclear capacity. So for folks who are aware, there's about a little bit over than 3.5 gigawatts of nuclear units online in New England. We run those for the purposes of supporting system stability as base load across the network. And what we're seeing here is that if the net load goes down in 2031 to below 2,000 gigawatts, then it's very likely that we're going to have to do something with the New England nuclear capacity that the capacity was not designed for. When folks have seen this slide in the past, people have said, oh, you could potentially ramp them like what's happening in France. That is certainly not what it's been designed for in terms of how New England runs those units. They run all the time. They are baseload. They do not ramp. So from the standpoint of the way that the system has been operated, if these net load days show up in 2031, we have to protect our nuclear units. That's really the essential function in many ways of the transmission system. And we recognize that as this net load goes down, if you just look at normal conditions, steady state, this is what we're going to be encountering. So this is a very significant trend in New England. Some other folks have said, well, hey, maybe you could export to New York. Well, this is from the New York control area. This is NYISO's forecast of their 2033 net load, and they're seeing the exact same trend as we are. So this is a very significant trend that in which the behind the meter solar within the whole control area, and then where we are in upstate, next to our upstate partners at NYPA and whatnot, they're going to be experiencing something very similar in terms of their solar output. So that's very significant. All right, so now I'm going to move on to some stability observations. And what I mean by stability is under disturbance conditions. So I'll be talking about those phenomena. All right, this is a screenshot from University of Tennessee, Knoxville and Oak Ridge National Laboratories FNet YouTube channel. This is actually from July 6th, 2022. This was an event in which the HVDC tie from New York to Quebec tripped offline. And what we experienced, as we would in any event of that magnitude within the Eastern Interconnection, is a frequency perturbance where in this particular diagram, normal frequency is red, the low frequency is blue, just for emphasis here. And so from the standpoint of actually being able to capture what really happened, we looked at this and said, wow, this was a very significant event from the standpoint of rate of change of frequency. And we saw something we didn't expect to see. And this was very important for us. So post-contingently, we saw after this disturbance, the Vermont net load increased by 50 megawatts, and we saw the New England net load increase by 100 megawatts. That was not predicted to happen. From the standpoint of evaluating SCADA measurements and SCADA errors, we did an extensive analysis of that point. We contacted New England, ISO New England, and we all saw the same thing. And the rate of change of frequency, as measured at one of our stations on the interface, was 1.25 hertz per second. Now, for folks who may be familiar with that level of rate of change of frequency, that's well outside of distributed energy resources ride-through parameters that are expected to occur. And even in 1547, 2003, it's actually not even spoken about in the NERC reliability guidelines. Do a great job capturing those ride-through settings and what's expected there. So what we saw here was post-contingently the net loads increase in response to this, and really our localized inertia within our area was far less than we expected to occur. So this was very significant. This had happened before in August 2019, actually in the United Kingdom. And what happened was there was an offshore wind farm that tripped offline, followed by some steam turbines chirping, and the frequency response was recovering. But then what ended up happening was that as other generators tripped offline, a embedded generation, what they call distributed energy resources, tripped offline in response to rate of change of frequency. And it was 200 megawatts. Now you can see with that red box there and that arrow going down that initiated under-frequency load shed protection. And when under-frequency load shed protection initiated, London lost power for 4 hours. So we are talking about the difference between a bad day to a really significant risk to public health and safety. The North American Electric Reliability Corporation wrote a lessons learned on this event and specifically called out transmission operators. That in particular was of great concern to NERC, of course, because we have requirements, as I will talk about later, to be modeling different events, different contingencies, and how that could end up affecting the system. And one of the more, I think, powerful figures that's included in the event report from National Grid ESO is their statement of time and events, their table of statements from time and events of every single statement that the organization made publicly. So you can see that they were asked by their regulator to provide time and date stamp for each statement, what they said, explaining what happened. So we are talking about a level of scrutiny within a utility that reaches not just in terms of engineering or operators or planners, but really across the entire enterprise. So this is a very significant event, and we can learn a lot from it in the United States. So our event in this regard was July 2022, right? And that's how much solar PV was online, right? And from the standpoint of that ISO New England figure, our nuclear units were running. That's what we saw. But what happens from the standpoint of when there's grid demand with so much PV that the nuclear units may not be able to run in that case, or they have to be taken offline seasonally, for instance? And what happens to the distributed energy resources in New York? And how does that affect power swings across inter-area dynamics? That becomes a very significant issue that we have to get out ahead of in order to protect reliability of the system. So now I'm going to go into FERC Order 901, which is really what FERC is doing about it, what FERC and NERC have underway to protect against these exact risks. So just as a refresh on the reliability responsibilities, as a transmission planner and transmission operator, we're required to study and prepare for contingencies. And the definition of contingency, right, that we are using is unplanned event, where you have an outage of a critical component like a transmission line, a transformer, or a generator. And in this particular diagram, you can see that this K19 line out, right, we planned for that, as well as this outage of a generator connected at East Avenue. And in this case, you can just see, we look at the system and we run a power flow analysis for this exact contingency to protect against a situation in which we are exposed. As also a reminder from transmission planners and transmission operators, We are doing contingency analysis in multiple timeframes. We do years ahead planning analysis for our TPL1 studies. We do day ahead analysis, our operational planning analysis for TOP2, and our real-time assessment, which is a TOP1 requirement. These acronyms I'm using, these numbers I'm using, these refer to NERC standards that we get audited on every 3 years. And so there are significant fines, penalties for not complying with this. And of course, we work very hard to meet these requirements all the time. What FERC Order 901 is doing, and I am getting a little bit of feedback from the room, I think we're a different caller, just so you know, but just as a heads up there. But what FERC Order 901 is doing is specifically looking at the definition of a contingency and saying, okay, from the standpoint of losing a generator, synchronous unit, right, you might have that covered, but really what we need to be looking at is aggregate inverter-based distributed energy resources, which I've depicted on this diagram just for simplicity, for the sake of understanding what's going on here. So to be more specific, using a diagram that I developed just to help communicate all of the new requirements that are coming, NERC is required to submit some new standards to FERC and in the November timeframe of the next 3 years. This coming November 2024, ride-through performance standard for inverter-based resources will be required. That will be like a vegetation management standard. I don't know if folks are familiar with that. Vegetation management, we have a performance-based standard that if in fact we have a tree contact that has significant fines associated with it, we take that standard very seriously. We're expecting a very similar type of requirement for inverter-based resources that if they trip offline, they could encounter fines and be very significant. So that's both at the transmission and now at the sub-transmission level for the BES and GEO IBR resources that are going to be connected. November 2025, we're going to be required to do model validation. So to not only have models of inverter-based resources and aggregate inverter-based resources, but actually have processes to validate those models. Is a very significant change from a lot of utility practices today, which are just getting ahead of modeling inverter-based resources. So we're going to be required to model and validate those models. And for November 2026, our contingency analysis requirements come in. And that is specific to those planning assessment, that operational planning analysis, and the real-time assessment that I mentioned. That's where those standard comes in. Now, for most NERC standards, it might take 5 years or so to become effective, especially for the November 2026 requirements. But FERC went so far as to say they believe that there's a need to have all of the directed reliability standards effective and enforceable well in advance of 2030. So this means that all the transmission planners, transmission operators around the country are going to be working to get technology and become compliant with these new requirements, which are very significant and require changes to the way that they've done business for many years. For folks who are interested in the specific language, here's paragraph 176 of FERC Order 901, which specifically calls out those studies that I mentioned and points to some of the effective NERC standards that they expect to be changed, namely IRO 10 and TOP3. So what are we doing? What are our plans? We're implementing a fiber reliability program in Vermont, in which we're extending our fiber network, as I mentioned earlier before, to connect to 68 substations, 485 DER sites, covering about over 400 megawatts of generation. And that has SCADA quality data associated with it that we'll be pulling back for watts, VARs, and voltage. We then will be routing that data to a tool called Integra, which is from AspenTech, and that will then be used to actually support our real-time assessments as well as our day-ahead operational planning analyses. And that will be mapped from SCADA and EMS to the operator tools so that they know that they can trust this information when they're making operational decisions. There is a very powerful function within that tool that allows us to have embedded data source selection. So we could say, okay, if DER telemetry fails, which is very possible, fall back to a nearby bellwether or meteorological estimate that's nearby. So we can have estimates of not just the DER 150 kW and above, but also the nearby residential DER that we would not have visibility into to create an aggregate distributed energy resource model for the state and to understand how that could be, the DER could behave. We're also implementing what's called the Vermont Exchange Platform, our VX Platform project. That's a single source of truth, common information model-based network model manager. And that actually was the basis of a lot of these slides that I presented to the SIM user group at PNNL. just a few weeks ago. And for this particular requirement, we're going to have unique identifiers for all distributed energy resources to support our modeling requirements. So for folks who may be familiar with how network model management works, this is just a little bit of a refresher. For folks who may not be as familiar with how these tools, different tools work, this is how it goes. You have an operations node breaker model. That's you can see here on the left-hand side. And ultimately, what we're going to do is map our operations node breaker model to our planning model and then to our protection model. So for the purposes of the equations that are run for the real-time assessment or operational planning analysis, we want to have breaker representation explicitly in there to protect safety, to protect operational configurations. Whereas our planners, right, they're running the Newton Raphson, they're running the power flow studies in our Aspen team, right, in terms of the fault current contributions at each of these different areas. They have a reduced model as well. But what happens is that the operations node breaker network model manager will have everything in there. And then we'll be able to make sure that the blue bus matches the blue bus, matches the blue bus, the red matches the red, matches the red. So this is the means by which of connecting all of our models together. This is a network architecture diagram we've shared with our stakeholders here in Vermont at the Vermont System Planning Committee meeting as well. And this shows how facility ratings changes to the system that are coming in. We get passed to our tools, PSS, ODMS, that then will create PSSE, create Aspen, create what we need for Node Breaker and Monarch. And we'll also be using a tool called Symphony for GIS sim modeling. And that's a really important tool for us to be able to have confidence, because a lot of the data that's coming in from the distribution utilities, we've understood that a lot of it will be stored in a GIS format. And we want to do whatever we can to help facilitate the ease of data sharing between distribution utilities and VELCO. So this is the architecture that will scale and help us meet our requirements. It's also really important that we stay very focused on transmission functions so that we can make sure that we can actually audit and validate. We will not have any control of any distribution assets or distributed energy resources, which could include an IBR or flexible load. We'll have SCADA EMS control points to prove that. Well, nor will we have any PII, personally identifiable customer information. We can be able to validate with database fields. But we do want to make sure we have what we need as a transmission operator and a transmission planner. That's very important. Big picture, collaboration is critical. I cannot emphasize this enough. Many of the interpersonal skills that you learn in school and you learn in your classes, working on group projects, are just as important as those technical skills that you work on. So I would really encourage students to really hone in on those. And this is a great example. What happened recently was that there's significant savings realized in Vermont from the dispatch of a virtual power plant. You can see Canary Media reported on $1.2 million being saved for Vermonters during this time. And that was saved using the dispatch of 4,000 batteries, residential connected batteries at the time, which was 20 megawatts of capacity. But the virtual power plant today is far, far more. So you can see the virtual power plant ultimately is dispatched, and we can see that aggregate performance. And what we need to do is collaborate with our distribution utilities who are realizing this value for Vermont and build systems that enable them however we can for them to perform that distribution function, for us to stay focused on transmission and stay in that role. So greetings from the frontier. As a follow-up for everybody, we are going to be required to meet the 901 compliance requirements. If you're interested in sharing ideas, I've talked to Wei, I've talked to Anamika. I'm really interested in looking at new ideas and partnerships across the board. What we're trying to do is go from the bottom left, the unknown unknowns, to the top right, to the known knowns. And the way we get there and incrementally make those steps and changes is through partnerships. So we're always looking for new ideas, new collaborations, and from there, happy to take questions. This is our planning team, and they do great work, and very grateful to be working with all of them. So thank you so much.
Okay, question. Maybe first we go with people online. So if you have questions, please unmute yourself and ask your question.
I do have questions, but I would prefer students to ask first.
Okay, let's go to a student first. Okay, we will come back to Wade later on. So, any question in the room? Want to ask question?
Yeah. So I just make sure I had it formed before I say anything. So looking at your observations early on, looking at how demand is going to drop below these base loads in the New England area. As someone who works closely in this area, what do you see as the likely solution in terms of what people tend to do in this area? And is that the same thing that you would recommend as someone more focused on the transmission side?
Yeah, thank you for the question. So I think it's helpful to sort of put into context just how many protections there are for nuclear power plants across the system. So we have NERC standards dedicated to protecting nuclear generators. Nuke 1 is the standard that is used to protect that, and there are many requirements in place that would actually result in a transmission planner studying this exact scenario and then evaluating all sorts of different options and technologies. So for us on our end, what we are working with the ISO, with ISO New England to do is to really bring all of the options to the table in terms of how transmission planning occurs. So we're looking at flexible load, battery energy storage, any number of other flexible assets that can be added to the system that can help us get more out of the existing system as it's set up. So for us, we want to make sure that the transmission planning solutions that are considered include all the solutions from a non-transmission alternative all the way to a transmission upgrade or say the interconnection of new generation. So for us, what we're focused on is let's make sure that the analyses, the planning studies that are done include all the different options that are technically capable of helping support that problem, and then make sure that the planners have those tools so they can make the decision on how to support the grid.
Okay, thank you.
I guess a follow-up on that question, is one of those solutions being explored potentially updating some of the nuclear power plants to have more flexibility, or is that something that on a technical level would be too difficult?
Yeah, it's a really interesting question, and one of those points where if that were to occur, that would require likely an interconnection study to look at that change in the operational characteristics. It would require, of course, the interconnecting generators to lead that request, and it would really be in terms of making sure that you protect safety and welfare of people. Of course, those assets are critical. And so from that standpoint, I think the studies we have the tools right now to do those studies. Whether or not these particular assets would elect to take that choice, it's a great question, and we can only look at what's happening in Europe and say, okay, there are solutions that have been considered in these various areas, and the New England stakeholders will have to determine whether or not that's the right fit for us.
Hey, hi, Dan. I wanted to ask if you are going to go into operations, like operational level, or is just planning level? And if operational, how do you think are you going to integrate load models? Like, because buildings and houses will have PVs, EVs, and storage. Like, how do you envision incorporating that in your product?
Yeah, so in collaboration with our distribution utilities, we're looking to find the best and most efficient data sharing mechanisms to really support the transmission functions. So you're absolutely right. We're going to have to do transmission operations with situational awareness of the aggregate behavior of those assets. So let's take a virtual power plant. Virtual power plant that's 40, 50 megawatts in Vermont that's composed of all these different technology types. Now for us, in order to not only study that in real time, we need to have situational awareness of what that virtual power plant is going to do. But we also, from a day ahead study standpoint, that TOP2 requirement, we need to have the ability to forecast what is that virtual power plant going to do next day. And then from a planning standard standpoint, 5 years from now, we have to ask, well, how is that virtual power plant going to behave? So we're going to need that for planning, day-ahead studies and operations, and we'll be figuring out from a data sharing standpoint the most efficient ways to do that type of data sharing. We're thinking GIS is actually going to be a very helpful tool in the toolbox to help support us. But that's what we're thinking.
And finally, it's frivolous, but I'll still go ahead and ask it. Is there anybody who is doing that for you? If not, I would like to come and do an internship next summer, if that's something.
We just wrapped up our internship program at VELCO, and it was a cohort model where the interns worked for operations planning, engineering, technology, and they actually were able to work on interdepartmental projects. So having stakeholders in not just one area, but working collaboratively together. So our internship program, which is called the Advancing Grid Intelligence Through Learning Experiences, the Agile internship program, is something absolutely I would encourage folks to consider as you're looking at your potential summer plans. And I'm sure you're not going to get any shortage of folks reaching out to you to say, okay, you learn these great things at WSU. How do you apply them in the real world? How do you apply them? And we're absolutely interested in building partnerships with you all as a feeder for your students. So please, Wei and team, just let us know how we can help support that.
Thank you. Thank you.
Hi, Dan. Great presentation, by the way. Can I inconvenience you and ask you to pull up one of the slides in your presentation, specifically the one where you are showing the IBRs in the grid, which you made at the 3 levels?
Yeah, absolutely. Stand by 1 second. I think this is the slide. Let me know.
Yep. So one thing I'm slightly unsure about, with all the great things you have presented. So you have talked about how you are concerned about adhering to NERC standards. And you also showed us basically duck curves of how behind the meter PVs are basically causing such a lack in demand that even your nuclear generation can be jeopardized. My question is basically how for example NERC standards for, let's say they operate at the interconnection level, so not something what I understand is behind the meter level, but let's say something which at the sub transmission level at the minimum they can basically you will have to run studies there. My question is for the behind the meter studies, one that are there robust standards for that? And second, if there are do they have to pass similar kind of scrutiny as, let's say, an interconnection study in terms of, let's say, for the low system strength, do you need to do a PSCAD analysis? Because you are several times mentioning that you have SCADA quality data, and which I understand won't be enough, right, for our usual interconnection study.
Yeah, so I'll break the question down into a few different parts, and you just let me know if I've hit all the points that you've made. It's a great question. So number one, the NERC standards are going to be changing to address exactly what you just said, to create robust standards at the distribution level. What I'm depicting here in terms of that yellow and that green down at the distribution voltage is that T&D interface at which we're going to need aggregate inverter-based resource and distributed energy resource models. That will be true, for instance, in our PSSE models, but it will also be true, as this next slide identifies, with the IBRs and DERs in the aggregate. We're going to actually need to represent those in our operational studies. So absolutely, that's something that's very critical. I'll go back here to the PSCAD question. So the Federal Energy Regulatory Commission actually considered but declined to require electromagnetic transient studies for these resources. And in what we have in New England, however, are some rigorous requirements for Planning Procedure 5-6, which require cluster studies. Now, cluster studies are done with a reduced area model of PSCAD in a particular zone of the system, in which we have, say, a concentration of inverter-based resources, distributed energy resources connected at the distribution level. And so for resources 1 to 5 megawatts that aggregate up to a total that affects the bulk electric system, those actually do get interconnection studies using PSCAD in New England. And NERC has pointed to ISO New England's practice of doing that through Planning Procedure 5-6 as being the best practice. We expect that we will have to do more and more of those studies, and that actually EMT studies, we're hoping, and I can actually show you here, more than hoping, we're planning to be building out our PSCAD capabilities. And you can see from our network model management diagram, we start with our node breaker model, we export to PSSE, and we'll actually be going to PSCAD from there. So we intend to be able to do network model management and model building based on this exact point. So electromagnetic transient studies are going to be very, very important for all operators and planners to be able to have access to and be able to do. Now, in terms of SCADA quality data, that's a tough one too. We're really looking forward to being able to have this level of coverage and situational awareness, and then from there, I think realistically we'll be able to assess what types of decisions we can make safely and reliably to protect the system, and then what types of other information we might be able to collaboratively work on to say phaser measurement unit or even data that's faster. We're actually looking at a startup that has basically DFR, PMU, RTU quality data that can be connected in, called Grid Metrics. And that startup actually collects data from the distribution secondary voltages at 10,000 samples a second. So what we're anticipating is that there are going to be many tools in the toolbox that we'll need to have in order to support model validation for the purposes of PSSE, for PSCAD, for PSS ODMS, and we'll meet those NERC requirements wherever they go. Just going back and jumping around a little bit, right? If we have model validation requirements for November 2025, we need to be making the strategic investments right now to protect Vermonters, to protect reliability, safety, and affordability of our network.
Okay, yeah, thank you so much for clarifying. I just maybe in a more as a much more general question, I just wanted to know that does like VELCO and let's say and whatever it operates on, does it have to like deal with like as part of let's say the duck curve you showed and how it is like getting deeper and deeper? Does it affect let's say like post disturbance? Does it affect the grid in similar how do I say like intense manner as let's say what ERCOT faces, or like behind the meter DERs are not as much like intensely affecting the grid stability itself?
Yeah, we are benchmarking our project and approach with ERCOT for that exact reason. We're in very similar situations in terms of the impacts of inverter-based resources. Rate of change of frequency is not uniform across the Eastern interconnection, nor as I think is it in WEC and the Western interconnection. But it certainly is the case in ERCOT that they're really far ahead and thinking about frequency-related problems. So if we can benchmark our approaches to ERCOT the way we're doing, that's a really helpful way to build trust among our stakeholders and be able to share with industry, right? Because we want to make sure we're implementing those best practices to keep people safe, keep the system reliable.
Thank you so much, and all the best on this.
Thank you. Thank you.
Yeah, just quick follow-up on his comment. For that aggregate model that you mentioned for the FERC requirement, do they require the dynamic aggregate model or not? That is at this point just...
Yeah, that's exactly what's required, is DER_A. FERC 901 requires every transmission planner to implement it.
Then what is the envisioned common practice for industry? Because I assume that all of this distribution system are a bunch of rooftop PV panels. So even do they have a dynamic model for that?
DERA, of course, is a component of the composite load model, right? As if you may be familiar with, right? There's the different motors, the electronic load, the different aspects of it. And so there's utility scale DER that's represented, and then there's also residential scale DER that's represented. So ISO New England has a appendix to their transmission planning technical guide on just this exact question. How do you implement DER_A? And what they've done is they've actually published, and now it's going to become enforceable in January 2025, a data sharing standard called Planning Procedure 12 that will require data sharing consistently across from distribution utilities all the way up to the ISO. So we're part of that chain. We actually are responsible to be providing the mapping from feeders from the distribution system to the PSSE load buses and to the EMS buses. But you're exactly right. There's going to be a lot of workflows that need to be established, created to keep those DER_ models up to date, to validate them with post-contingent event analysis. And we're working collaboratively with our distribution utility owners, as well as with ISO New England, on what these new model validation transmission and event analyses processes should look like. So Xiaoshuan at the ISO is a great collaborator, and we're really grateful to be working with him and his team.
Oh, nice. Yeah, that is interesting problem to work on. So
yes, hopefully it's so interesting. They have research teams who are working on it, and they can help us out. In a way, and I just talked about this recently, so I'm grateful.
Oh yeah, Ray, you want to say something?
Yeah, so this is very, very interesting question, and I'm very glad Saeed asked this question. And Dan, thank you for introducing FERC Order 901. I printed it out and read page by page, so I learned a lot from that. But I think the DERA model in the FERC Order 901 is very challenging. They ask them for aggregate DERA model. Yes. To represent aggregate distribution behavior with DERs. But then you know that right, distribution utilities, they don't do dynamic simulation at all. And the transmission guys, you do dynamic simulation. Now you are going to move to EMT. But when I talk to distribution utilities, they use SIME. They only do the quasi-steady state simulation, and they never have those DER models. And then it's very hard to develop very accurate aggregate DER models. I think this is not just say FERC requires and everyone is able to do that. I think there are still some challenges there. A lot of research is needed to really think about how to model that.
I couldn't agree more. More research is needed, and we have to reach out to our software vendors, let them know what's coming, so that when they're trying to build their product roadmaps, they understand what those requirements mean for us and how we can collaborate. So I'm totally on board. I think more and more analyses that are done that build confidence in the system so that we can provide reliable transmission service, those are needed. And where we can work collaboratively with distribution entities to figure out standardized data sharing across the interfaces, I think that will go a long way to building that trust in the models.
Yeah, I think, exactly. I think distribution software vendors need to have that kind of dynamic simulation capabilities and very good DER models there. Like SIME, I don't believe SIME do that, but most utilities use SIME and Synergy. None of those tools offer this kind of simulation function, dynamic simulation function. I think that's a very interesting area we need to
get the word out.
And industry.
Let's get the word out. We'll share with everybody. We gotta do something about this. We need the tools to step up and really provide the solution to meet the regulatory requirements.
Yeah, and another, thank you, Dan. Another question is that when you have IBRs, bulk power system connect IBRs, when you work with those developers, what kind of models you require them? You require both PSSC and the PS guide model, right? Or okay, so you have all their black box user-defined models. That's a good thing. And also I noticed that you're right. The NERC, FERC, they decline to use EMT models at this time. But I think it's always good to have some EMT models to do some small system studies. I don't think we need to go to the full EI system with PS guide, but for your local study, you can build a small system to see how.
I think everyone's watching Australia. Everyone's trying to get a better understanding of how their system-wide EMT model and approach is working. We're also looking at ISO New England, right, in terms of how they've done clusters of approaches, and there are many different ways to use EMT, and we're very grateful for all of the insights that folks are publishing about the right way to do these studies. I would say that this is what you just flagged, the way, is a really important point for students to be aware of, is that PSCAD is not going away. Is a very important tool in the toolbox, or EMTP or electromagnetic transient tools in general, right, are going to be a really key component to how we keep the system reliable with inverter-dominated systems. So all the work you've done in grid forming inverters, and no, seriously, it's critical. We need to get out ahead of it. And if we don't have more situational awareness of what the models are doing, then we don't have accurate studies. If we don't have accurate studies, then our operators don't have all the information to make great decisions.
Yeah, thank you very much for this presentation. I learned a lot from their practical point of view on how this real transmission planning works. I hope that will be very beneficial for the students. Thank you.
I hope so. Yeah.
And can I ask for your slide?
Oh, of course. Yeah. No, I'll send them out.
Okay.
Yeah.
Thank you.
More question?
There was a question here.
Oh yeah. I thought that you're my student. I thought that you're Hassan. Where is Hassan? Oh, that's you.
So I just have a question out of my curiosity. I noticed that those drops in the net load, they happen around 10 a.m. to 2 p.m. So if you look at the timeline. So around noon time, which is basically, it shows that It's coming from the solar plants that you have there. So what about wind energy? Do you also have much wind there? And what is the approximate share of the wind and solar capacity that you have?
We do have wind in Vermont. For the most part, I would say that New England wide, right? It's a relative to ERCOT, right? Just to be clear, right? It's a relatively smaller resource, but that's changing with the proliferation of offshore wind and the amount of offshore wind that's about to be connected. Our system is really going to be experiencing some very significant differences. So part of that interconnection of that wind, what it represents is, in addition, that added complexity. So yeah, my slides do not cover that, but what you're looking at with California, with Texas, there's a certain level of uncertainty there with those flexible resources. Hopefully wind can help, maybe hybrid resources too. But from the standpoint of how wind plays in, you're correct. My slides don't go into that yet, but offshore wind is coming, and we expect it to play a key role in the energy transition.
Thank you.
Thank you.
One question? You still have some time, so. Who is the lucky person? Wanna go for last? Yeah, you are lucky one. Yeah, go.
Yep, so, hi Dan. I saw in one of your slides that you are investing into around 800 miles of optical fiber communication in between around 65 substations.
Mm-hmm.
Yes. And as you do that, I think the whole point of doing all this is to make system more reliable with more and more penetrations of DERs into the system. However, I do not see how we can be sure the system would be more reliable, because we are making system more vulnerable as well with dependency on the data. So hello.
So I do want to make sure I didn't interrupt you.
Okay. So if we are being really dependent on the data, and especially data from the distribution center, and we are still figuring out how to model that distribution system model itself with the DERA and everything you mentioned. I did not look into that, so I'm not very sure how it works.
Absolutely. So data privacy, data protections, data governance are absolutely key to the success of our projects. I cannot emphasize that enough. And what we're finding is that with more and more of these distributed energy resources, you're talking about a system that without situational awareness, we're not going to be able to make those decisions to protect the grid in the event of a contingency. So there's a balance, just as you've identified, in which we need to, as I mentioned, have situational awareness of those distributed energy resources, 150 kW and above. But what software we chose has a backstop mechanism in it, so that if the data quality is in fact out of the limits or outside of the range of what we would determine to be normal and acceptable, we will actually have the ability to fall back on flags automatically to tie to a meteorological forecast and or a bellwether a site that's nearby, so that we can protect against a situation in which that data quality is out of whack. So that is a really important design consideration of the solution that we've gone to, because it protects against exactly what you've just raised, which is how do you protect the system when you're relying on so much data? You do it with these fallback mechanisms to say, if this source fails, then what, right? So you prepare for the contingencies in terms of data quality, just like you would with the contingencies in terms of the transmission network. So that's a design type of thinking that we're very accustomed to at a utility, and we've embedded that design consideration right into our solution. It's a great question. Very important.
No question?
So thank you for answering the question. And just to follow up on that, you said it's really important, and you rely on the flags, then you go back to it, and then you, what I would say, reset. If you detect a bad data, you reset the process up to a certain what could I say, a certain flag, a certain timestamp, and then you redo the process. So I assume this all is going in a centralized manner as of now. Yes.
Well, from the standpoint of the solution that we'll be implementing, yeah, it would be implemented with a tool that's just like the operational technology that we have from a SCADA EMS standpoint. So yeah, absolutely. It would be that function would be something within our electronic security perimeter, for instance, that we protect against. Yeah.
This would be a centralized process. So you'll be doing centralized planning, then the centralized operation, then the real-time study. Everything would be centralized.
I'm not sure I followed which word you just used.
Centralized.
Centralized.
From the operations perspective, I'm
Right.
talking about the control perspective as well. So we have a centralized setup here. Yes?
From a monitoring and situational awareness, but there's, as I mentioned, right, there's no control of distributed energy resources in our situation because we're transmission only. And so as a transmission only entity, we need to have situational awareness, monitoring of those assets, so we can then make decisions based on the power flow equations. And so what I think you're also getting at here is like, what if the centralized system goes down, right? We're going to build a design into our design exactly what you're, I think, getting at here is we need to protect against that exact contingency. What do we do? How do we use the least known, the last good value, for instance, of in our topology? Because ultimately, with utilities, there's always a backup plan to the backup plan, and then you just keep going from there. So that's part of the standard design.
Good. Thank you so much for answering that. Thank you.
Yeah, thank you. It's great. Good thinking, because cyber physical questions in terms of the integration of exactly those types of points, I think more and more we need to be anticipating what happens when operational technology does not perform the function as designed. And so I think the question that you're asking reflects to me, frankly, that you guys are doing really well at Washington State to get the questions to your students to say, what happens when these new systems go into service? How do you protect against it? A utility needs to be ready for that exact scenario. So great to see that, and very impressive that you're thinking that way.
No question, Roma? Okay, that was excellent presentation. We really appreciate that. Always that's nice to see the people from industry and see how in reality you guys implement different methods, different strategies. That was really nice presentation. I appreciate it.
Thank you. And thank you so much for the invitation to present. And please reach out. You have my email if any other questions come up. Happy to talk through. And I look forward to catching up soon.
Sure. Thank you. And have a great day. Okay.
Take care.